Okay, so let's talk about how we're going to do this. When you have a chemical reaction, it is called a reaction because it involves a chemical change. A chemical change because our atoms that are reacting are going to form new combinations, and these new combinations are going to have new properties. So we are taking one or two substances and we are making something different. We are not just evaporating, condensing, so changing the color. We're not doing any of that. We are actually changing what they're doing. So we're going to use a chemical equation to represent our reaction. So we're going to use our chemical formulas. So that means you have to be able to name it or to write the formula from the name to indicate the reactants and the products, and we're going to use coefficients to show the ratios. That's a lot of words. Let's break it down. The reactants. The reactants are going to be the initial substances. What you start with, what is doing the reacting. You might hear my drawl come out because a lot of times, to keep from confusing myself, I call these reactants. That's okay. Reactants is probably the more correct way, but I lived in Alabama for a while, so. Now, reactants always go on the left side. Reactants, what you start out with, they go on the left. So it's like reading. When you read from left to right. Products. These are going to be the substances that are formed as a result of the reaction. And they go on the right side. And then we separate them with an arrow. So reactants and products are separated with an arrow. Now, coefficients. Students, myself included, when I first learned how to do this, you will want to change the subscripts. We don't ever change the subscripts, we use coefficients. Coefficients are whole numbers and they're the regular size text. So they're not little exponents and they're not subscripts. So they're whole numbers and they go in front of the chemical formulas. And they are going to balance the number of atoms or moles of atoms, depending on how you want to look at it. It means the same thing, of each element on both sides of an equation. Now, why does it have to be balanced? Oh, I know. It has to be balanced. That means you have to have the same number of each element on both sides. That is because matter is not created or destroyed. So if you have two oxygens on one side, you better have two oxygens on the other. I'm going to help you. When you're writing your equation, you have your reactants. You may also hear them called reagents. I don't use that term, but some textbooks do. And products always go on the right. So when you're going to balance an equation, first thing you do is you write what the book calls a skeletal equation. That means you just write the chemical formulas out and you put your reactants on the left, your products on the right, and you separate them by the arrow. In order to do this, you have to write or copy the chemical formulas correctly. That's why I spent a long time on nomenclature. Because if you can't name something, go from formula to name or name to formula, you're going to have a lot of trouble with this. Now, generally, you can come up with your own strategy, but one of the easiest ways to do it is to balance atoms in the more complex substances first, which You go, but wouldn't it be easier to balance the simple ones? Nope. So I like to start with the elements that appear only once on each side. So if you have 2 on one side and 2 on another, and 1 on another, it's not balanced. So you obviously need to put a 2 in front of the one where there's only 1. Then you move on. Then, as you're going through that, you want to balance the atoms that occur as the free elements, because those are easy to change. When you get done, you want to double check that your coefficients, so the numbers that you put in front, are in the smallest whole numbers. So as you're going through this, you may have something and you're going to have your coefficients say 2, 2, 2, 4. That's not the smallest. The correct answer would be 1, 1, 1, 2. But depending on how you get there, and it's okay if you get there, you just have to go back because you want the smallest whole number ratios, then give yourself a double check. Now, when we do this, I brought my pencil because I need an eraser. Even though I do this a lot, that's okay. I do it a lot by trial and error. Now, this is your reminder. Use coefficients. Only ever use coefficients. Do not ever change the subscripts. All right. Now, there are some methods that will teach you to use a chart, and if you want to use a chart, it's totally fine. I think that takes entirely too long, but if that works for you, great. So I'm going to look here, switching to my pencil, and kind of start going across. All right, well, all of these only appear once on each side. So let's just start somewhere. Start from the left. All right, this is nitrogen. How many nitrogens do we have on the left? 1. How many do we have on the right? 2. So it's not balanced. So we need 2 nitrogens on this side. So let's make this a 2. It may or may not stay a 2, but put it in there for now. Okay, let's move on and look at oxygen because it's the next one. How many oxygens do we have now? 2, because this is a 2 times the subscript of 1. Is anybody confused why I did that? Why we have 2 oxygens? We have 2 oxygens on the left. How many do we have on the right? Only 1. So this needs a 2. Let's move on. How many hydrogens do we have on this side? 2. How many do we have here? 4. So multiply your coefficient by your subscript there. So that means we need a 2 over here. Now we've gone from left to right. I put blanks in front of everything when I ask you to do this. If it makes you feel better to put a 1, do it. If you don't want to, just leave it blank. It's understood. If it's blank, it's understood to be a 1. Some people like it, some don't. I don't care. So let's do a final check. How many nitrogens? 2, 2, 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens, done. Does that make sense? We've done this before? Good. All right. Now, this next one, you can start wherever you want, really, but it's easier to start with the most complex substance. So this looks like the most complex to me. But if you want to start, again, how you get there really doesn't matter. But I'm going to look at this and go, oh, that's going to be trouble. So here there's 3 oxygens. How many oxygens do we have over here? Only 1. So let's put a 3. How many aluminums do we have? 2. There's only 1. So let's put a 2. Now, our only other substance is iron. Here there's 1. How many are over here? 3. That's fine. It's easier to do those ones those free elements that are just by themselves last, because you can change them real easily. And then this is a 1. In case you need that. So double check. 2 aluminums, 2 aluminums, 3 irons, 3 irons, 3 oxygens, 3 oxygens. Moving down to the next one. It is okay to work ahead of me. I won't get offended. Alright, this one here. This looks like the most complex. And oxygens on both sides. So let's look at that. So how many oxygens do we have over here? 3. How many do we have over here? Oh, can we balance that with just 1? No. So what should we put here? What is our least common multiple? If we have 3 and 2, how can we get them the same number? 6. So we have 2, so that means this needs to be a 3. So now we have 6 oxygens. And here we have 3, so this needs to be a 2. So we have 6 oxygens. Anybody confused? Did I lose anybody right there? Okay. Now, let's look at iron, I guess. Alright, so how many irons do we have on the left now? 4. So all by itself on the right, so that makes it easy. Let's put a 4. That leaves us with carbon. There's 1 and 3, so that needs to be a 3. Did anybody learn how to do this using the chart method? Okay. It's okay if you do, that's fine. Alright, so double check. 4 irons, 4 irons, 6 oxygens, 6 oxygens, 3 carbons, 3 carbons. Good. Now, when you get to equations that have polyatomic ions, you can balance the equation by the elements, but I like to treat the polyatomic ion as like a single unit. So this is how my brain works. My brain says I'm going to start with a polyatomic ion and say, how many sulfates do we have? 3, because that's easier than 12 oxygens and stuff. All right, so we have 3 sulfates. How many sulfates do we have over here? Just 1. So I'm going to make that a 3. I think that goes faster for me, considering them as one single unit. All right, next, would you rather do aluminum or hydrogen? It doesn't matter. Aluminum. How many aluminums do we have on the left? 1. How many over here? 2. So let's make that a 2. Hydrogens, we have 2. How many do we have over here? 6. So you could also say how many H2s do I have, and you can say 1 and 3 if you prefer that. That's okay. You can leave this blank, or you can put a 1 there. It doesn't matter. Alright, sodium phosphate, magnesium chloride gives us magnesium phosphate and sodium chloride. Where should we start here? Phosphate, that's where I would start too. Alright, so there's 1 over here, 2 over here. So let's go ahead and make that a 2. Okay. Sodium. I guess we might as well do that one next. Sodium, there are now 6. There's only 1, so let's make that a 6. So we've done sodium, we've done phosphate. I guess let's do chlorine next. So we have 6 chlorines right now, only 2 on this side. So if we have 2 and we need 6, we multiply by 3. Check magnesium, 3 magnesiums, 3 magnesiums. You can put a 1 if you want to. Is this coming back? If you've done this before, yes. If you haven't done this before, are you thoroughly lost? Nobody's admitting it. Okay. All right. Next ones. Lead 2 nitrate, aluminum bromide, lead 2 bromide, aluminum nitrate. Practice naming them. All right, where should we start? Nitrate. All right, what should this one be? Because we have 2 of them over here, and we have 3 of them over here. So this needs to be 3. Yeah, we need a total of 6. So now we have 6. We need a 2 to make that 6. All right, where do you want to go next? Lead or aluminum? Oh, aluminum? Okay, let's do aluminum. 2 aluminums, 1 aluminum. Need a 2. It doesn't matter, it's gonna work out the same. All right, you're gonna do lead or bromine. Bromine, okay? So we have 6, we have 2, okay? And then double check the lead, 3 and 3. Everybody with me? Yes. All right. Now, let's talk about types of reactions. Types of reactions are helpful when you're determining what your reaction is going to look like. So there are 5 types. I'm going to give you some examples of them. The first one is called a synthesis, or you may hear it called a combination reaction. This is where you have 2 or more elements or compounds, and they react to form one product. So generically, the reaction would look like reactant A plus reactant B forms, they get smushed together. They are combined to form one product. You are forming a new product. Practically, you can have sulfur and oxygen, and that will give you sulfur dioxide. This helps when you're given a word equation and asked to write the formulas and balance it. Next one, you can take uranium and you can take fluorine. Notice this is fluorine because it's an element. This is not fluoride. And that will give you uranium hexafluoride. Is this balanced? No. Now it is. Next one, decomposition. It's the other way around. In a decomposition, you have one reactant splits into 2 or more. So you may have more than 2. 2 or more simpler products. So generically, you would start with compound AB, and it decomposes into substance A plus substance B. The book doesn't talk about this very much, and I think it comes in really handy when you're working a word problem. Next, let's have calcium carbonate. It's going to decompose into calcium oxide and carbon dioxide gas. Is that balanced? Yes, it is. If you're not sure, just count them. 1 calcium, 1 carbon, 1 carbon, 3 oxygens, 1, 2, 3 oxygens. This is probably the first example where we've had oxygen in multiple compounds. It's okay. One side has to equal the other side. So 3 and 3, it still works. Next, mercury 1 oxide decomposes to liquid mercury oxygen gas. Hg. Is it balanced? No. Now it is. All right. Next one, single replacement. This is where one reacting element or ion switches places with an element or ion in the other reacting compound. So generically, if you have A plus BC as your reactants, one of these is going to switch places. So let's say it looks like AC plus B. Now, how do you know which one? Which one switches places? Well, whichever one is by itself, you have to determine, is it going to form a positive or a negative ion? In this generic reaction, I decided it was going to be a positive ion, so it replaced the positive ion in the compound, in the other compound. So here, to look at it this way, zinc plus hydrochloric acid. All right. Hello. Does zinc make a positive or a negative ion? Positive. Hydrogen is also positive, so that's going to make, so zinc's going to switch places with hydrogen. Zinc's always +2. So you may have to write your charges. Hydrogen is diatomic, so it's always H2. When it's by itself, is it balanced? No. Now it is. All right, let's do another one. If you have copper and silver nitrate, copper is going to switch places with what? Silver, because they both form positive ions. In this case, because it doesn't tell you, it would tell you in a it's copper, copper 2, and silver goes by itself. Is it balanced? No, it's not. What should we do to balance it? We need 2 nitrates on the left, yes. Now we also have 2 silvers, so that means we need 2 silvers on the right. Next one, a double replacement. You can say this 2 ways. I'm going to tell you the way that I like to do it. I say in a double replacement, the positive ions in the reacting compound switch places. You could also say the negative compounds switch places, but it depends on how you want to write it. You'll get the same answer. But for me, it's easier to change the positive ones. So if you start with 2 compounds the positive ones switch places. So A goes with D and C goes with B. If in your mind that was the negative one switching places, that's fine. You get to the same place. Now, what does this look like? If you have barium chloride plus sodium sulfate making barium sulfate. So see, barium now goes with the other one. And sodium goes with chloride. So do you see the positive ones switch places? It's kind of like a square dance. Change partners. I'm old enough that I had to learn square dancing in elementary school. All right. Is it balanced? No, it is not balanced. All right? But that balances it. Another example. Phosphoric acid and sodium hydroxide react to form positive ones switch places. So sodium phosphate, and now here y'all are gonna not like how I do this, but this is an OH, and when it switches places with water, I write water when I'm balancing equations as HOH when hydroxide is involved. If you want to write it as H2O, that's fine, but I write it as HOH because then I can balance my hydroxide as a polyatomic ion. If you don't like that, you'll get there the same way. But that helps me keep track of things because I have hydrogen in 2 places. Helps me out. So to balance this one, where should we start? We can start with phosphate because it's a polyatomic ion. 1 phosphate, 1 phosphate. Great. All right, sodiums, 3 sodiums, 1 sodium. Uh-oh. But now that gives me 3 hydroxides, 1 hydroxide. Then I can get 3 hydrogens, 3 hydrogens. So that makes it a lot easier for me to balance them when I have hydrogens and oxygens in multiple places. That's where I'm not a fan of the chart method, but if you like the chart method, do it. But double replacements when you get these polyatomic ions can get a little bit tricky like that. Now, last type of a reaction we'll talk about is a combustion reaction. Combustion is where you have a carbon containing fuel. So something that is carbon-based always burns in oxygen from the air, and it's going to produce 3 things. It's going to produce carbon dioxide, it's going to produce water, and then it's going to produce energy in the form of heat or flame. So if we take C3H8, do we agree that this is a carbon-based compound? Yes, it's actually propane. You don't have to know that. You do not have to know how to name organic compounds for me. All right, it's going to burn in oxygen from the air. So when it says burns in oxygen, that's always O2. And the products are always going to be carbon dioxide. Here, since we're not dealing with hydroxide, I'm writing water regularly. Again, how you want to do it is fine. Now, you can get some really big numbers here. So I like to balance the carbons first, then the hydrogens, and the oxygens last. So to balance these, carbon, 3 carbons, so that means I need 3 carbons. Hydrogens, 8 hydrogens, 2 hydrogens. Now I have 8. All right, now how many oxygens do I have? 6 plus 4. 6 plus 4 is 10. And I have 2, so this needs to be a 5. I'm going to see if I can find one that doesn't work so evenly. And try a different one. Let's see if we do C4H10 plus oxygen, because I want to show you an example of sometimes it doesn't work that easily. These are large numbers. This may work out. I haven't tried it though. No, it won't. Okay. So 4 carbons. Now I have 4 carbons. 10 hydrogens. 10 hydrogens. Now how many oxygens? 8 plus 5. 8 plus 5 is 13. Is 13 divisible by 2? No. All right, so when that happens, you go, I can't do it. Here's the way to do it. Just write for now, write 13 halves, because that's what you're trying to do. Or you can write 6.5 if you want. This is, now we can't have fractional coefficients right now. We'll deal with that later. Okay, now how can we get rid of this half? We multiply everything by 2. All your coefficients by 2. So this becomes 2 C4H10, 13 oxygens, 8 carbon dioxides, and 10 waters. So you may not have to rewrite the equation, but balance your oxygens last, and if you end up with needing a decimal where you have an odd number of oxygens, write it over 2 and then double all your other coefficients. Wanted to give you that because it will come up, and most people absolutely hate balancing combustion reactions for that reason. Anybody have any questions about reactions? Okay.